Couple of things to bring up. First of all, I just got a notice that those of you that are going to be attending class in Richmond, I know the network isn't up there today, and there's a room change. You guys are going to be moving next door starting Monday. I believe you're going from room 141 to 143 or the other way around. Just so you're aware of that, so you're not surprised when you show up on Monday and the room that you're used to being in is tore apart. Apparently, it's either part of the construction or too close to the instruction to be usable for a classroom for now. Next, we have the test. All of you should have received the test back. Those of you that are here and that took the test here on Rice Lake, I gave you the paper copy back at the beginning of class. Those of you in New Richmond or Superior, you should have received it in your email. Actually, I had them graded by the end of the day Tuesday, so you should have received them in your email Tuesday afternoon. I managed to have a little extra free time, so I got them done. Well, actually, what it was is all the ones from the other sites were actually here by 12:30 Tuesday afternoon, so I graded them. Normally, sometimes it's at the end of the day or even the next morning before I get them. So anyway, if you opened it up in your email and all you saw was your test and you didn't see any of the markings on it, try to open it on a computer within the building at WITC. I use an ink program to write on your tests, and sometimes if you don't have the correct version of Word at home, you cannot see the ink. So any of the computers at WITC, if you open it up in the building, you should be able to see the ink. And many of you will be able to see it at home. But anyway, if you have that issue, use a WITC computer and hopefully it'll show up. If it doesn't, let me know and I can just tell you what problems you have wrong. I have them saved on my computer. Also, now that you have them back, you are not done. If you like your grade and you want to just go with that, you are welcome to, but you have the option, and I highly recommend it, of redoing the problems you have wrong. Those of you in Rice Lake here, you can just redo them right on your paper and hand them to me. Those of you in New Richmond or Superior, you can either redo them on the paper and take them to the LRC or the ITV office and have them rescan it and email it to me. Or you can just send me an email saying, okay, number 4, I was wrong, and here's, type in the email step by step how you do the problem and get the right answer. So you do have to show work. Normally on the test, I don't require you to show work for credit, but when you're correcting the problems, I do require you to show your work so I know that you're doing the right thought process and not just looking at the person next to you who got the right answer. But this, I will give you up to half of your points back for that. So now, a C is considered to be 79.9 or 79.5% or 80% basically. So let's say you got a 60%. If you do corrections, that puts you at that 80%. So you're right there. So it's a great way to get points back. So everybody in the class will be passing if they do their corrections. If you have questions on the corrections, I don't mind if you work with a classmate on them, just as long as you are writing down step by step how to solve the problem. It's kind of my sneaky little way of making you look at it again and making sure that you at least have the correct process down somewhere so you can look at it later. If you can't find somebody to help you with it, come and ask me. I would be happy to step you through them step by step as to how to solve them. I just want to make sure that you've at least seen how to do each problem correctly before it's done. For that reason, I'm not going to go over the tests in class today. If there are still questions on Monday or Tuesday, I will be happy to go over them with you. Okay, so on that note, it is time to start in with more new material. We kind of reviewed our algebra and applications to geometry in the first hour. Now let's take a look at a little bit new material. And what we're going to look at here is I want to look at something called divisibility. That's kind of an odd looking word. There's a lot of I's in there. Divisibility means that one number goes into another number without a remainder. For example, 21 is divisible by 7 because you can divide 21 by 7 and there's no remainder. Now there are other numbers, of course. 21 is also divisible by 3 and whatever. If you're asked to list factors of a number, factors are all numbers the number is divisible by. I suppose if you want to be technically correct, it's all numbers by which the number is divisible, but this is math class, not English, so I don't care. For example, factors of 36. Well, 36 is divisible by 2. It's divisible by 3. Is it divisible by 4? Yep. Is it divisible by 5? No. If we divide by 5, there's a remainder of 1. How about 6? Yep. 7? No. 8? Careful. 8 would be 4.5. That's not, or 4 with the remainder of 4. 9? Yes. 10? No. 11? No. 12? Yes. Probably tell by the tone of my voice that one's 13? No. 14? No. 15? 16? No. What's the next one? 18. 18 is the last one. You know how I know that? 36 divided by 2 is 18. I can't get any bigger than that because I can't multiply by anything smaller than 2, right? Without getting into decimals or fractions. Those are all the factors, all of the numbers that 36 is divisible by. Now, if I ask you to find factors of, let's say, 24. Now, I didn't say list the factors. I said find factors of. Well, factors are numbers that it's divisible by, but it can also be just pairs. I mean, I could possibly look at like, well, 2 times 12 is a set of factors of 24. 3 times 8, or even 4 times 6. All of those are sets of factors of 24. Now you might be thinking, how about 1 times 24? That multiplies to 24. Yes, it does, but we don't count the 1. Anything can be 1 times itself. So to avoid, stating the obvious, we don't count that really as a set of factors. Factors have to be numbers other than 1 or itself. So anyway, we've looked at these divisibility and these factors. Leads us to 2 types of numbers. There is something called a composite number, and there's something called a prime number. Now the word prime means beginning or main number. Prime means it's not made up of smaller components. It is a building block of its own. So prime numbers are not divisible by anything other than 1 and itself. For example, 11 is a prime number. There's nothing that divides into 11 other than 1 and 11. 17 is a prime number. 23. Now I left a lot of them out, didn't I? We got 2, 3, 5, 7, 11, I already named 13, 19. So these are by no means all of the prime numbers. There's an infinite number of prime numbers. And those are some of them. So a composite number can be broken into smaller factors. And I've already looked up here what I mean by factors. So I guess one of the big questions is there an easy way to tell if a number is prime or composite? I mean, after you've worked with numbers long enough, there's some that you just know that can't be divided by anything. But when we look at something, is there an easy way to tell if it is divisible? Well, there are some divisibility rules. I can look at a number very quickly and tell if it was divisible by certain basic numbers. For example, how do we tell if a number is divisible by 2? Well, the last digit of the number is even. What do I mean by even? It's a 0, 2, 4, 6, or 8. In other words, the last digit is divisible by 2. Is 37,914 divisible by 2? Yes, it is. 219 divisible by 2? No. Three is a little trickier. Does anybody know the rule that we can use to look at a number to tell if it's divisible by 3? Not the last digit, no. Because like 21 is divisible by 3, but 3 does not go into 1. They're not necessarily all odd either. We actually look at the sum of the digits. Well, what does this mean? Well, let's look at the 3,719. Sorry, 37,914, I should say. If I add up the digits, what is 3 plus 7? 10 plus 9? 19 plus 1? 20 plus 4 is 24. Is 24 divisible by 3? Yes, it is. What if you didn't know that? What's 2 plus 4? 6. Is 6 divisible by 3? Yes. So 24 is divisible by 3, and therefore 37,914 is divisible by 3. That's kind of cool because you actually keep going as many times as you want to until you get down to a number that you either know is or is not divisible by 3. So if I had 512,391, is that divisible by 3? Is it divisible? Yes, those digits add up to 21, which is divisible by 3. 4? Well, 4 really isn't that important because if it's divisible by 4, you can just divide it by 2 twice, right? So if it's divisible by 4, it's going to be divisible by 2. But you can actually tell if something's divisible by 4 looking at the last 2 digits. So, for example, let's say I have 92,332. All that I care about is the 32. Is that divisible by 4? Yes, so this whole number is divisible by 4. The problem with this rule is this. If I am trying to figure out something like 7,188, how many of you have your multiples of 4 memorized up to 100? All right, I didn't think so. 88 is divisible by 4, so that is divisible by 4. But again, it's not necessarily an easy rule. But you can look at that and very quickly tell it's divisible by 2, so you know it at least has factors. Well, the next one's one of the easy ones. How can you tell something's divisible by 5? Last digit is 5 or 0. Very good. So again, it doesn't matter what the rest of the number is. I can have 72,915,375. All that we care about is it ends with a 5 or a 0. So that's divisible by 5. Six. To tell us something's divisible by 6. Again, the rule isn't that important because if it's divisible by 6, you can divide it by both 2 and 3, right? And so you just divide by 2 and 3 and you have it done with. But actually, that's what the rule is. You can divide by both 2 and 3. So let's take a look at that. 2 and 3. You have to be able to divide by both. Let's see if I did that right. That should work. So now the first thing I'm going to check, which one's easier to check for, 2 or 3? 2. So I'm going to check by 2 first, because if it's not divisible by 2, there's no use going through the trouble to check for 3. Is this divisible by 2? Yeah. The 4 is even, so it's divisible by 2. So the 2 is good. How about 3? Well, 5 plus 8 is 13, plus 1 is 14, plus 4 is 18. So yes, 18 is divisible by 3. That is divisible by 3. How about this one? Well, if I wanted to add up the digits, I could. I'm actually going to get 18. So it's divisible by 3, but I'm not even going to bother to do that. Why? Last digit's not divisible by 2, so it's not divisible by 2, so it cannot be divided by 6. So it has to be both 2 and 3. How do you tell something's divisible by 7? Watch a lot of football and memorize the different touchdown projections. I'll let you off the hook. There is no rule that I know of for testing if a number is divisible by 7. So here's the challenge I put out there for you. If you can develop a rule to tell if a number is divisible by 7 that works every time and is simple like the ones we have up here, and show it to me, and it works, I will give you an A for the course for the summer. Because I'm going to publish it, get rich, and retire. So I think that's a fair trade for me. So anyway, there is no rule for 7. How about 8? Well, again, 8 doesn't really matter because you could just divide by 2 3 times. You divide by 2 over and over again, you divide out the 8s. But there is a rule for 8 is the last 3 digits. So let's say I have 5,271,136. To tell if that's divisible by 8, I'm just going to look at those last 3 digits. Is 136 divisible by 8? Well, this one's even less useful than the 4 rule, isn't it? I mean, you have a chance of maybe figuring out the multiples of 4 from 0 to 100. I'd really doubt that any of you have the multiples of 8 memorized from 0 to 1,000. 136 is divisible by 8, by the way, so this number is divisible by 8. But again, at that point, you're probably going to have to type 136 divided by 8 in your calculator. So why would you not just multiply, type in the whole number and divide by 8 and see if you get a decimal? 9. Almost exactly the same as 3. Except, of course, it's the sum of the digits is divisible by 9 this time. So 21,413 is not going to work. 411 is what I was shooting for there. 21,411. Is that divisible by 9? Well, yeah. 2 plus 1 is 3 plus 4. 7 plus 1. 8 plus another 1 is 9. And 9 is divisible by 9, so 21,411 is divisible by 9. 10 is an easy one. How can you tell if something's divisible by 10? Last digit is a 0. So it doesn't matter what anything else is. 473,249,610. All that matters is that digit right there is a 0. So it's divisible by 10. Now I've already mentioned like the 4s, you can just divide by 2, so it doesn't matter if it's divisible by 4, you're going to just divide by 2s anyway, most likely. Same with the 8s, you can divide by 2s. Even the 9s, you can just divide by 3 twice, and you've divided out 9. So as we get larger, I mean 10 even you can divide by 5 and by 2, but 10 is a really simple one. As we get larger, they don't bother having rules for numbers like 12, because you can just divide by 2s and 3s and divide out all the 12s. 15, you can divide by 3 and 5. And 16, of course, you can divide by a bunch of 2s. So the only ones that even make sense to have rules for are the prime numbers. And many of the prime numbers do have rules for divisibility. The problem with those rules is they are extremely ugly as you get into larger numbers. In fact, once you get above 10, the rules are actually more difficult than just dividing it out. The one for 11 I'm going to show you just let you see just how ugly it could get. But it's really, there's a point where the rule is so difficult it's not worth remembering, is the point. So to tell if something's divisible by 11, you do every other digit. So let's take a number like 508. Now let's just do 58,377. To see if that is divisible by 11, you take every other digit. So I start with the 5, so that'd be the 3 and the 7. What do those add up to? 15. Then you take the remaining digits, 8 and 7, add up to 15. Then you subtract these two. If the difference is 0 or divisible by 11, then the number is divisible by 11. So 58,377 is divisible by 11 because the difference is 0. So let's take a look at another one here. So let's try this one. So I've got 5, 3, 1, and 1. What do those add up to? 10. Perfect. And then I have 8, 7, and 6 add up to 21. What's the difference between those? 11. I didn't say what order you had to subtract. It's always the biggest one minus the littlest one. Difference is 11. That whole thing would be divisible by 11. Now again, that's not a real easy rule to remember, is it? Probably not one that's practical. The only reason I remember it is I'm a math geek and it interests me. But realistically, after the next 10 minutes, I don't really expect any of you to be able to apply that one. With the calculators, you don't have to. You can just punch it in and divide by 11, and if there's a decimal, you know that it's not divisible by 11. And again, as we get larger, there are rules for many of the other prime numbers, but they get more and more complex as you go. So we're not going to mess around with them. So let's get back to this whole idea of factoring. Well, actually, let's do this. I want you to look at those 5 numbers. I want you to list any factors for each of those numbers. If it has no factors, label it as prime. I'll give you a minute to try it, go through that. 32, first of all, is it prime? No, it's not. What are some of its factors? 2, 4, 8, and 16. And 16, of course, is half of it, so we know that's the last one. 57, is it prime? A lot of people want to say so, but 5 plus 7 is 12. It's divisible by 3. Then, of course, to find the other one, just divide it by 3. 19. 3 and 19 are the 2 factors of 57. That gets, almost everybody tries to say that one's prime. Because most of them are. 17, 37, 47, those are primes. So I want to jump on 57. 17, I just gave that one away. It is prime. How about 41? It is prime. There's nothing that divides into 41. How about 51? Five plus 1 is 6. It's divisible by 3. And how do we find the other one? Now, if you just did 51 divided by 3, you would get 17. So, a lot of numbers that when you at first glance, your mind would want to think they were prime. If you look a little closer using those divisibility rules, you'll see that they're not. Now, when I'm using the divisibility rules, what I do is this. I always progress through them. The first things I look for are 10s and 5s. Why would I do that first? Because it's really simple. 0 or 5 at the end, and I've got it. The next thing I look for is a 2. Because again, that's really easy. I just have to look at that last digit. Is it even? And if it is, I know it divides by 2. After those, then I look for 3. And usually that's all I have to do. If none of those, if it's not divisible by any of those, then that's when I'd look for like the odd ones, like 7s, 11s, 13s, and stuff like that. Very seldom will I give you like 13 or something like that. Unless you guys really, really upset me between now and a test. It's not very likely to see a 13 or something. So we talked about factoring, creating those pairs of factors. But let's say I ask you to factor 48. There are several pairs. We could have 2 and 24. What's another one? 3 and 3 times 16. Any others? 4 times 12. Very good. All of those would be factor pairs of 48. So the question is, which one would I want? Well, for that reason, we don't usually just ask for you to give me a set of factors. What we usually ask for is prime factor. The prime factors means you're going to break the number down into the smallest numbers you can, no matter how many of them it takes. So you're going to break it down into prime numbers. Notice here, 2, 3, and 4 are prime, but 24, 16, and 12 are not, which means each of those could be broken down further. How do we do that? Well, we make a tree. And the cool thing about this is it doesn't matter where you start, you should end up with the same result. So I know that 48 is divisible by all of 2, 3, and 4. Could have had 6 times 8 as a set of factors here, by the way. 2, 3, 4, and 6, and 8, and 12, and 16, and 24. There's all sorts of pairs of factors, all sorts of numbers that are factors. Pick one of them. Give me a number that divides into 48. 3. So if I start with 3, because I know it divides into 48, what is 48 divided by 3? 16. Good. Now I look, is the 3, can that be broken down any further? No, it's prime, so I'm going to circle it so that I know I'm done with that. 16, of course, can be broken down further. It can be divided into 8. Okay, 8, and then what would be left if I did it 16 divided by 8? What's left? 2. The 2 is prime. I'm going to circle it. 8, however, can be split up into 2 times 4. 2 is prime, so I'm going to split up the 4. The 4 is 2 times 2. There's nothing left to split up. So the prime factors of 48 are, I usually list them from smallest to largest, 2 times 2 times 2 times 2, 1, 2, 3, 4 2s, times 3. So that is one way to list the factors of 48. Another way I could list them would be this. Instead of listing all 4 2s, I just list 2 to the 4th power times 3. Either one of those is acceptable. Now, my math lab, it may ask express it as exponents or whatever, so you got to make sure you're paying attention to that. If it says express it with exponents, it wants it this way. So let's practice. We'll do one more example here together. I asked you to prime factor 60. So I'm going to make that 3, 60. Now remember, I gave you that progression I go through. I always look for 5s or 10s first. 60 is divisible by 10. The reason I do that is because if you take out a bigger number first, it actually shortens up the process. Because now both 10 and 6 can be split up. 10 can be split into what? 5 times 2. Both of those are prime, so I'm going to circle them. 6 can be split into 2 times 3 or 3 times 2. Both of those are prime, so I'm going to circle them. So we have our prime factors there. So 60 is equal to 2 times 2 times 3 times 5. Or 60 is 2 to the 2nd power times 3 times 5. Again, either way is acceptable. Any questions? What's that? They looking too easy? No? Oh, come on. Let's have you prime factor 42 for me. So I'm going to walk you through progression here. Can 42 be divided by 10? No. 5? No. 2? Yes, it can. So I'm going to divide by 2. 2's prime. I'm going to circle it. What's left over if I divide it by 2? 21. Okay. And usually it's that first number that's the toughest. Once you get it divided by something, then it's usually easier. Now it's relatively easy to see that 21 can be divided by 7 and 3, both of which are prime. So 42 factors into 2 times 3 times 7. Yep, that works out. It doesn't matter whether you start with a 2 or a 3 or a 7 even. You end up getting the same result. So let's have you prime factor. Let's do 180. Give that one a shot. See what you come up with. So when you look at the 180, what is the first number that sticks out right away that you can divide it by? 10. And if I divide it by 10, I am left with 18. Can the 10 be split up further? Yes, it can. It can be split into 2 times 5. Both of those are prime, so I'm going to circle them. 18 can be split into 9 times 2. The 2 is prime. I circled the 2. How about the 9? 3 times 3. So 180 factors into 2 times 2 times 3 times 3 times 5. Or 2 squared times 3 squared times 5. Either one of those is acceptable. Again, you have to be careful. If my math lab asks for it to be in exponents, you do have to put it in the powers. Any questions? Not so bad? So you might be wondering, how did we jump to this factoring stuff from working with the variables? Hopefully it seems a little bit easier to you. Well, because factoring is a huge key in finding some important things in math. Talk about common factors. Common factors. Let's say I have the numbers 12 and 16. Well, if I listed out the factors of 12, and I'm going to assume at this point you guys can do the factor trees. So I'm going to take a shortcut and not do the factor tree and just list out the factors. 12 is 2 times 2 times 3. (16), its factors are 2 times 2 times 2 times 2. If I prime factor it. Now you look there and you can see they both have 2's in common. Now there's a weakness with this because they have other factors in common that are not prime. If I listed just the factors of 12, there's 2, 3, 4, and 6 are all factors of 12, right? Factors of 16, I got 2, 4, and 8 are factors of 16. What they have in common are the 2's and the 4's. Those are common factors. Normally, I am not concerned with just any old common factors. I am concerned with something called greatest common factor. From here on out to be known as the GCF, so I don't have to write so much. The greatest common factor is the largest of those factors that divides into both numbers. Well, I have 2 and 4, that would be the 4. So the question is, I just did all this fuss about doing prime factors. Can I get the greatest common factor from those prime factors? And the answer is yeah, I can. The greatest common factor is a combination of all common factors. So if I look up here, they have a 2 in common, but they also have a second 2 in common. If I do 2 times 2, I get 4. So let's say I have 48 and 60, and I want to find the greatest common factor. Well, what I'm going to have you do for me right now is I'm going to have you guys prime factor both of those quick so that we can look at the greatest common factor for those two. So 48 factors into 2 times 2 times 2 times 2 times 3, correct? Should be 4 2's. 60, 2 times 2 times 3 times 5. So now let's see, what do they have for common factors? There's a 2. Is there another 2? Yes. Is there another 2? There's another one here, but not in the 60, right? So no, there's only the 1. Anything else? A 3. So our greatest common factor, 2 times 2 times 3. 2 times 2 is 4, times 3 is 12. 12 is your GCF. So I'm going to have you guys try to find the greatest common factor of 90 and 150. See what you come up with. So when you prime factor 90, what do you get? 9 and 10, but you gotta keep going. So you got 2 times 3 times 3 times 5, right? I always go smallest to largest. Prime factor 150, what do you get? Perfect. 2 times 3 times 5 times 5. So what they have in common? 2, 3, and a 5. 2 times 3 times 5 is 30. So the greatest common factor is 30. What do you think? Better than variables in geometry? Okay. So that's the greatest common factor. There's another thing called common multiples. Common multiples, a multiple is a larger number that it goes into. What's that mean? Well, it's actually a lot simpler than it sounds. Multiples of 6 are 6, 12, 18, 24, 30, 36, good, 42, blah, 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 blah. Counting up by 6s. Multiples of 5s would be 5, 10, 15, 20, and so on. Guess what? Our prime factoring can help us find multiples as well. Because something we often look for is something called common multiples, as we just said. Let's say common multiples of 6 and 8. Well, 6 we just listed, 6, 12, 18, 24, 30, 36, 42, 48, 54, and it would keep going. Common multiples of 8 would be 8, 16, 24, 32, 40, 48, 56, and those would keep going. So we have 24, there's 48, there'd be 72, 96, and they'd keep going. There'd be an infinite number of common multiples here. So we don't want to list all common multiples. Normally, what we're working with is something called the least common multiple. Otherwise known as LCM, so I don't have to write that out anymore. Now, a lot of people have a hard time remembering the difference between GCF and LCM. Greatest common factor. Greatest means you're looking for something that's the largest. Well, if you're looking at multiples, the largest one would be infinity. It would just keep on going forever. So if you're looking for something that's the greatest or the largest, it must be something smaller than both numbers. You're looking at the factors. If you're looking for the least common multiple, you're looking for the smallest of the numbers that are bigger than them. So the least common multiple here is the 24. So the question is, how do I use my factors to find that? Well, 6 factors into 2 times 3. 8 factors into 2 times 2 times 2. There are a couple of ways we could look at this. To me, it's easier to do easiest to do the least common multiple if I write them in powers like this. Okay? So I have 2 times 3, and the powers there are actually just 1, right? Then this is 2 to the 3rd power. The least common multiple includes all of the factors, no matter what. So it's going to include the 2's and the 3's. And their highest power. What's the largest power on the 2? 3rd power, right? 3. Highest power on the 3 is just 1, right? So the least common multiple is 2 times 2 times 2 times 3, or 24. That's the way I like to think about it because that works quickest for me. Now another way to think about it is this. They both have a 2, right? They have that in common. This one has a 3, doesn't it? Does the other one? No, so this one needs a 3. So now they both have a 3. I'm just going to circle the ones that they have in common, right? Is there anything that's still not circled? Yeah. How about down here? This one has a 2. This one needs another 2. Well, there's still a 2 not circled, so this one needs another 2. Now they have all the same factors. You see what I did? I just went through the factors, and whatever one had that the other one didn't, I gave that to the other one. So now this is 2 times 3 times 2 times 2, which is 24. 2 times 2 times 2 times 3, which is 24. That is the least common multiple. Let's practice that a little bit. Find the least common multiple of 12 and, oh, what do I want to do here? Let's do 20. So my first step is going to be to factor the 12, 2 times 2 times 3, and to factor the 20, 2 times 2 times 5. Now that I've factored them, my second step is going to be to circle any common factors. What do we have in common? We have a 2, another 2. Now I look at the ones that are uncircled, and I have to force them to be in common. This one has a 3, and this one does not, so I'm going to put a 3 here. What else do I need to do? Put a 5 on the first one. Now they have all their factors in common. Well, I know that this part here was just the 12, right? 2 times 2 times 3 times 5 would be 60. This part's just the 20 times 3 is 60. They have to make sure they come up to the same number. 60 is the LCM of 12 and 20. Want to try one? Sure. Why not? Find the LCM of 12 and 18. So the factors of 12 are 2 times 2 times 3 18 is 2 times 3 times 3. How many of you came up with those factors? No? Okay. Well, that's half the battle is getting the right factors down. From there, I'm going to pause for a second. Now that you have the right factors in front of you, go through and see if you can find that least common multiple. So we have the 2 in common, and we have a 3 in common. What else do we need to do? We need to put a 3 up here. So now the 3 and a 2 down here. So 36 and 36. Very good. Now you can, if you forget how to do the factoring thing, you can always do just, okay, 12 and then 24 and another 12 is 36 and 48. And you can do 18 and 36. Hey, I found the match. That will always work. So you can always fall back on that if you forget how to do the factor. So you might be wondering, why am I putting all this effort into factoring and greatest common factors and least common multiples? Well, because the moment you've all been waiting for, and I'm sure possibly a reason why many of you are in the course, the main purpose of Unit 2 is fractions. Factoring and fractions go hand in hand. We've already talked a little bit on the first day about fractions. Or if we have something like 3/4, so that 3 is called the numerator, and it is just the count of the number. It's telling us we have 3 of something. The 4 is the denominator, and it is our name telling us what it is. Just like having inches or cows or pounds, we have fourths here. So the 4 isn't really a number, it is a label or a name. So to start off with, we need to define really what it is to be a fourth. Probably the simplest way to do that is to go back to the old elementary school illustration. Pretend that's a circle. Take a pie or a pizza or whatever you want to do, and you divide it into 4 equal pieces. Pretend these are equal pieces. Each of those pieces is a fourth. So when we have fourths, you can think of it as one of two things. Either every whole object is cut into 4 equal pieces, or it takes 4 of those pieces to make one whole object, kind of looking at it from different sides. So that's what it means to be a fourth. For this to be 3/4, then that means that we have 3 of those pieces. Yeah, I know I'm not going to win any awards for my coloring. What's that? Oh well. Like I said, I'm not going to get first prize for the color. So that's 3/4. One of the things we need to do in order to work with fractions is we need to be able to rename it. The easiest way to rename a fraction using this illustration is to simply do this. I can cut each of those slices into equal pieces. Let's say I'm going to cut each of them into 3 equal pieces. Pretend these are equal pieces. I'm drawing pictures, which means we're going to do a lot of pretending. So pretend those look equal. Now, how many pieces does it take to make a whole object? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? Each of these 4 was cut into 3, so 3 times 4 makes 12 pieces to make a whole object. How many pieces do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. We had 3, and each of them got cut into 3 to make 9 pieces. So this is now 9/12. Do we have any more or less pizza than we did before? No, it's exactly the same amount. It just looks different. And when we rename a fraction, that's what we're doing. We're not changing the amount. The amount is staying the same. We're just changing the appearance. 9/12 and 3/4 are exactly the same amount. They just look different. And the way we did that, the way we changed that was right here. We multiplied both the numerator and denominator by the same number. So the first thing we need in order to do that is we need to know, we're not just going to randomly multiply the top and bottom of the fraction by a number. We need to know what it is we want to change it into. So let's say I have 2/5, and I tell you I want to change it into 30/5. What I need to do is I need to figure out what do I multiply a 5 by to turn it into a 35. Or if it's easier to think of it this way, what is 35 divided by 5? Yeah. So that gives you 7, right? So 5 times 7 is 35. So what do we have to do to the 2? It must also be multiplied by 7. So 2 times 7 is 14. Now 14 35ths and 2/5 are exactly the same value. They just look different. So if I give you 1/3 and blank 12ths, what number is going to go up there? Perfect. Because 3 times 4 makes 12, or 12 divided by 3 equals 4. I must also multiply 1 times 4 to make 4, so 4/12. So I want you to try this one in your notes. See what you get. So what do we get? 10, perfect. 8 times 2 makes 16, or 16 divided by 8 makes 2. So you multiply the bottom by 2, you multiply the top by 2. So 5 times 2 is 10. Any questions on those? So now we can rename the fractions by multiplying the top and bottom by the same thing. What if we want to go the other direction? Call it reducing or simplifying. We might have something like 48 over 60. Well, let's, like up here, we just multiplied both the 5 and the 8 by 2 to get 10 and 16. If I wanted to reverse that, I would just divide both of them by 2, wouldn't I? 10 divided by 2 is 5. 16 divided by 2 is 8. It just simplified it down. Again, it's still the same value. I just made it look different again. So down here, if I want to reduce or simplify this, I just have to ask myself, what can I divide both 48 and 60 by? Now, at some point in your schooling, you were probably told you must find the largest number that divides into both of them. And that was a lie. You can find any number that divides into both of them. Now, the largest number, by the way, would be that greatest common factor. But we don't need to do that. We could factor them out and find it if we wanted to, but we don't have to. But what we can do is just find any number that divides them. Well, they end in a 0 and an 8, which means they can both be divided by 2. They're both even. What's 48 divided by 2? 24. What is 60 divided by 2? 30. Now, usually after you divide it by something and make it smaller, it becomes easier and easier to see what they can both be divided by. Now here, I can see that both of them can still be divided by another 2. 24 divided by 2 is 12. 30 divided by 2 is 15. Now I can't divide 15 by 2 anymore. But now that they're smaller, I can see that both of them can be divided by 3. Very good. 12 divided by 3 is 4. 15 divided by 3 is 5. And I cannot divide those both by any, there's no more common factors for you. In fact, 5 is prime, so I know I'm done. So 4/5. Now, had you looked at this right away and saw that both 48 and 60 could be divided by 12, you would get that all in one step. 48 divided by 12 is 4, 60 divided by 12 is 5. But again, that saves some work, but you don't have to do the greatest common factor. You can just find any common factor and you're going to get there. So I want you to try, let's go back down here. Reduce 35/50ths. What can both of those be divided by? 5. Very good. 7 and 10. How many of you had 7/10? Cool. How about 45 and 75? Try that one. What can both of those be divided by? You can see right away they can both be divided by 5, right? 45 divided by 5 is 9. 75 divided by 5, 15. Now I can see both of those can still be divided by 3. 9 divided by 3 is 3. 15 divided by 3 is 5. So I do get 3/5. Now you might be wondering, okay, if I'm not going to use that greatest common factor, where does factoring fall into this? One way I could go about this now, if you're good at what I just showed you, shut me out here if you want to. I don't want to confuse you. But there's an alternative way of going about this. I can take 45 and factor it. It's 3 times 3 times 5. 75 is 3 times 5 times 5. Now, the greatest common factor is the common factors, right? There's a 3 in common and there's a 5 in common, right? What's left over after you reduce a fraction? The ones that are not in common. So let's say I had 12/20ths. 12 is 2 times 2 times 3. 20 is 2 times 2 times 5. So I have the 2 and another 2. What's left is the 3 and the 5. Well, I should do that. I can cancel out, cross them off if I wanted to. How are we doing so far? Okay, well, I see that the meters are getting close to full, so I'll wrap this up as quick as I can. But there is one thing I want to mention. How would I reduce this? Zero. How would I reduce that? 56. Can't. This is saying it takes 8 pieces to make a whole object, and we have none of them, right? That's possible. It's okay to take 8 pieces and not have any of them. This, however, is saying it takes 0 pieces to make a whole object. That's not possible, is it? Or a fraction can be thought of as a division problem. We talked about this last week. 0 divided by 8 can be done, can't it? 0 divided by 8, if you punch it in the calculator, will just spit out 0. 6 divided by 0, however, your calculator is going to give you an error. We cannot divide by 0. Bad things happen. At some point, if I have some extra time, I'm going to show you a little bit of what can happen if you're allowed to divide by 0. Really strange things happen. How about this? Yeah, it's saying it takes 9 pieces to make a whole object, and I have 9 of them. In other words, I have one whole object. What if it was this? It's still 1. It doesn't matter whether these are numbers or variables. Anything divided by itself is 1. Yeah, I could use like 17 y to the 5th over 17 y to the 5th. It's still going to be 1 because it's the same thing divided by itself. Whenever the numerator and denominator are exactly the same, it's 1. Okay. What happens when we have something like this? Well, this is saying it takes 7 pieces to make a whole object. We have 43 pieces, which means we have more than enough to make a whole. In fact, we can make several whole objects. How do we know how many? Well, we said that a fraction can be thought of as a division problem. So if we try that, if we did 43 divided by 7, you get something like 6.142857143, approximately. Don't worry, it's not contagious. What does that tell us? Teacher has too much time on his hands. It's not memorized. I'm calculating it out. Remember I mentioned earlier that math is about patterns. Calculations are about patterns. Once you start to see the patterns, the calculations are easy. So you start to do the calculation and then you see the pattern and you just keep going with the pattern. That's telling me I can make 6 whole objects. The part after the decimal is telling me that there are pieces left over, but I don't know how many. Well, what's 6 times 7? 42. So I used up 42 pieces, which means there is 1 left over. There's 1/7 left over. Technically what this is it's a division and a remainder. This is 43 divided by 7. 7 goes into 43 6 times. 6 times 7 is 42 with a remainder of 1. So this is 6 whole objects, and this is my 7ths that are left. So let's say I had 33 fifths. I would do the same thing. 33 divided by 5. How many times does 5 go into 33? 6. What's 6 times 5? 30. So 33 minus 3 left over. So that is 6 3/5. So I want you to reduce 33/7. So 7 goes into 33 how many times? 4. 4 times 7 is 28, so there is 5 left over. So there's 4 whole objects and 5 of the 7ths are still left. This, by the way, is what we call an improper fraction. And this is what we call a mixed number, because it mixes whole numbers with fractions. The whole numbers are the number of whole objects, and the fractions are the pieces that are left over. I'll do one more. 25/4. Tell me what you get. 25 divided by 4 is 6. 6 times 4 is 24, so there is 1 left over. That's 6 1/4. Let's go the other direction. What if I give you that you have 3 4/5? So but I tell you that I want to change this mixed number into an improper fraction. Now, by the way, the word improper implies that there's something wrong with it. There's nothing wrong with it. We just don't like having, we like having things simpler. So it's simpler to have whole objects than it is to have a bunch of pieces laying around. Yeah, what we're going to do, what we have to do here is we have to break down these 3 whole objects into pieces. Well, how do I know how many pieces are in each of those whole objects? The denominator tells me that each whole object has 5 pieces. So 3 times 5 is 15. So this is 15 pieces, plus the 4 that were already there is 19 fifths. Oops, come back here. So if I have 7 3/4, I want to turn that into an improper fraction. How many pieces are in the 7? 28. 7 times 4 is 28. Plus the 3 is 31. So let's say you have 5 2/7. Turn that into an improper fraction for me. First of all, the denominator is going to stay 7ths. The denominator never changes unless we rename it. So it's, 5 times 7 is 35. Plus 2 is 37. What do you think? Better than a sharp stick in the eye? Well, does this help a little bit? Yes. Good. That's what I want to hear. Okay, so let's look at one place where these fractions are used. Let's go to circle graph. And let's look at hours in a day. I'm going to make my circle bigger because I can't write that small. I'm going to make my facsimile of a circle bigger because we know it's not going to really be a circle if I draw it. Pretend that's a circle. Let's look at the fraction of the day that the average student spends doing different activities. So the most important one in here, sleep. Let's say that's 8 hours. Class. So that is 6 hours. Studying. So that is 4 hours. And then let's see here. Let's put leisure. Put that as 4 hours. And then our remaining 2 hours is miscellaneous. Might be housework, might be whatever. So there's our 24 hours in a day. What fraction of a day does the average student spend in class? Now, normally the first thing we would have to do is we'd have to add all these up to get a total. Since this is a day, we know that the total better be what? 24. So there's 24 total. How many of them are in class? 6. So the fraction is 6/24. That can be reduced. Both of those can be divided by 3. Okay. 6 divided by 3 is 2. 24 divided by 3 is 8. Are we done? No. Both of those can still be divided by 2. Just 1/4. They spend 1/4 of their day on average in class. Actually, that's not much. I had days when I was in college where I spent 14 hours in the classroom. Oh, yeah, I'm not saying I was very useful those last 4 or 5 hours. Actually, I have days here where I spend 14 hours in the classroom. I have days that I start at 7 in the morning and don't get done until 9 at night. Any questions? There is a new quiz due tonight at 11:59 p.m. And there is a new homework due Monday. You are welcome to stick around and work. The network will stay up till noon. I will get these videos processed and posted as soon as I can because of the outage in New Richmond. Remember the room change in New Richmond for next week. Otherwise, have a good weekend.